Okay, so we're going to pretty much pick this up right where we left off on Monday. And we're going to start with talking about conditions for estimating mu. Remember in 8.2 we were estimating proportion, and now in this lesson we're using quantitative data and estimating the mean. So we have these checks for conditions, just like we did in the previous lesson with proportions. And to some degree, the conditions are similar ones to check, but there's minor differences, so pay attention for those. So condition number 1, just like with proportion, is that random condition. So you have to have data that's come from a random sample or a randomized experiment. With that goes the 10% rule, and that's just, again, like it was in proportion. So when sampling without replacement, which is almost all the time, you have to check and make sure that the sample was less than or equal to no more than 1/10 of the total population. Okay, finally, there's the normal large sample condition, and in proportion, it was just a large sample, and we use the central limit theorem. Well, with quantitative data, when we're estimating mu, we have 3 checks we can use for this. And the first one that works, all you have to do is use one of them. So the first one is if you're told that the population has a normal distribution. So if that's given in the problem, then you can say this is met. Okay, let's say that has not been told to you. Well, then the second thing to check would be, just like with the central limit theorem, that sample size is large, meaning it has to be at least 30. Okay, and then the third condition we only use if neither one of the first two would work, and that would be to take your sample, which is small, okay, less than 30, and graph it. And then you look at that sample graph and determine, is it approximately normal? Now, what are you looking for? You're looking for a single peak, you're looking for approximately symmetric, and you're looking for not skewed, or at least only very slightly skewed, and you're looking for no outliers. So if you see outliers, it's an instant no, it does not meet the condition. As far as determining, well, what's slightly skewed and what's strongly skewed, there is no hard and fast rule, but a little rule of thumb you could use would be if you go from the minimum to the median and from the median to the maximum. Okay, so you're looking at the bottom half of the data versus the top half of the data. If one of those is twice the other one, then it's definitely strongly skewed. So, for example, if your median was 100 and your minimum is 70, okay, well, the difference between the minimum and the median is 30. And then your maximum is 200. Well, then there's obviously more than 3 times as much spread on the right side of the graph as there is on the left side of the graph, so it's strongly skewed. So this little rule of thumb, it fits, at least 2. Now that's not any hard and fast rule, but at least it's a guideline for you to determine, well, is this only a little skewed or is it too skewed? Okay. Notice again, there are 3 ways for checking for that normal large sample. You need to know all 3. Also remember, you have to write these conditions that you checked them each time there's a problem where you are estimating mu. The problem will probably not tell you to check for conditions. It's expected that you know that. Okay, so then constructing a confidence interval. We've met the conditions, and the sampling distribution has roughly a normal shape, but we don't know the standard deviation. And notice this is sigma. We don't know the population standard deviation. So we estimate it by using the sample standard deviation. So this is how we do it. So the standard error for the sample mean, and the sample mean we use x bar, remember, instead of mu, is the standard deviation of the sample divided by the square root of n, and n being the sample size. So this then is what we use for that standard error piece in the formula for our confidence interval. Okay, so here's our little rules. Replace the standard deviation of the mean by the standard error, which you see the formula for just above here in the green stripe. And all right, and then use critical values from the t-distribution. So t star, remember that, and you use n-1 degrees of freedom. And then here's our formula, which is going to look very much like the one that we had for proportion, except instead of p hat, we have x bar. So we have x bar, which is sample mean, plus or minus t star, which is that critical value we get from the table or from our calculator, times, instead of standard deviation, we have the standard error, which is the standard deviation of the mean divided by the square root of the sample size. Okay, so you do need to remember that what we're doing right now is called a one sample t-interval for a population mean. What we did in the previous lesson in 8.2 was a one sample z-interval for a population proportion. So you notice that these are for when you have one sample. Guess what? We're going to do it for when we have more than one sample. But this is for when you have one sample, okay? And then on this screen, you just see a repeat of that formula for the one sample t-interval for a population mean. Excuse me. So here's an example. I'm going to ask you to pause this recording and read the problem so that you know what it is. And now we're going to go through the four-step process for actually constructing our confidence interval. Get used to this four-step process. We'll be using it for inference from now to the end of the year. It is very important. It is expected that you will use it, and it will help you to be thorough. So first of all, you have to consider, well, what is the problem? What is our parameter? We want to estimate the true mean of NOx emitted by all light-duty engines. Okay, if the conditions are met, we should use a one sample t-interval. So we check to see if it's random, and it said it was a random sample of 40 engines. We check the 10% rule, and we know that we had 40. Well, 40 would be 10% of 400. So I don't know about you, but I don't know if there are 400 different light-duty engines. So we just have to assume that there are, or otherwise they would tell us that there weren't. And then as far as a large sample, we don't know if the population distribution is normal. They didn't say it in the problem, so we have to go on to the next test. Because the sample size is large, which is 40, that's greater than 30. So central limit theorem says we're okay, and we can use our t-distribution. Okay, so step 3 is do, and so now we actually put it all into the formula. So from the information, we know what the sample mean was. We know what the sample standard deviation was. So to find the critical value then, we go to our table, and they told us that we wanted a confidence interval, or confidence level, of 95%. So at the bottom of the table, and you can look at this in the back of your book or in the handout of formulas, but at the bottom of the page you find 95%. Since our sample size was 40, we subtract 1, and then use our table, but you notice that 39 is not listed under DF. So since 39 isn't there, we cannot use 40. We can't go up. You always have to go down. So for our degree of freedom, we're going to use 30 since 40 isn't there. So going up from 95 to where the degree of freedom is 30. Excuse me, I should remember that. And we get 2.042. Now the thing is when you actually do this, when you do it on your homework, when you do it on the test, it is preferred actually for this that you use the calculator. The reason being is you can get more precise. You notice the degree of freedom, they skip numbers here. Well, in your calculator, you can put in 39. So going to your calculator, you're going to go second, bars, and then t interval, inverse t. And for your percentage, you're going to put in the 0.025, which you see at the top of this column, because that's just one tail. There are two tails, and they use the upper tail because then they get the positive number instead of the negative number. The negative number would be just the opposite. It would be the same number but negative, and then you would just use the positive. But you'd put in the 0.25, and then for the degree of freedom, you'd put in 39, and then you would get this more accurate number of t star being 2.023. Okay, well, on the presentation here, they've used the table, and they've got 2.042, so we will use that for now, but generally better to use the more accurate number from the calculator. So here's our formula on the left, x bar plus or minus t star times that standard deviation of the sample over the square root of our sample size. And then all the numbers are filled in, and you just do the follow order of operations to get this interval. And as far as interpreting the interval, you interpret it the same way. You draw the same conclusion as we did with proportion. And you have to put it in context of the problem. We are 95% confident that the interval from 1.1599 to 1.3751 grams per mile captures the true mean level of nitrogen oxides emitted by this type of light-duty engine. That's all I'm going to put into this recording, and then I'm going to make a second recording that will finish this lesson up.